Okay, this is the video that we're going to use to conclude Chapter 12. The instruction part of this video will be over 12.6 and 12.8, but you can stop the video now if you would like and check your homework over section 12.5. I have the work for these problems, the solutions worked out and attached to your homework page on May the 5th. And I also went ahead and attached the solutions to the 12.6 and 12.8 homework to your assignments page on May 9th so that you will know if you get those right as you work on those today. So take a minute, you can stop the video and check your homework. I also told you that I would go over Euler's theorem of geometry or rule of geometry. We're not going to get hung up on that word, but Euler's or Euler's, I've heard mathematicians, good mathematicians, use either pronunciation, but I really do think it's Euler's. Rule for geometry. Okay, all it tells us is if we have a prism, then the number of faces of the prism, that's the flat surfaces, plus the number of vertices in the prism, that's the corners, will always equal the number of edges, that's where flat surfaces come together, plus 2. So our faces, let's identify as, why don't we just use red for the faces? The faces, let's see how many we have. A face is a flat surface, so we're going to have the top, and we're going to have this side, and then we have this side. We have the 2 on the back, so that's 4 and 5, and then we have the bottom surface. So we have 6 flat surfaces or 6 faces. So with the faces, we have 6. Now, as far as the vertices goes, we said the vertices are the corners. So we have 1, 2, 3, 4, 5, 6, 7, and then we have an 8th one back here that we can't see, but it surely is back there. I'm going to dot in that side. Okay, that's not perfect, but it may help a little bit with the dimension. So we counted 8 vertices. So our 6 faces plus our 8 vertices is equal to 14. Now the 14 should equal to the number of edges plus 2. So for our edges, let's use, how about if we use the green for edges? Let's count our edges. We have 1 edge, 2, 3, 4, and then we have the 4 on the bottom. It's 5, 6, 7, and 8. Now we have our vertical ones. 9. The one at the back is 10, the one up here in front's 11, and this is 12. So we have 12 edges, and 14 is equal to 12 plus 2. So Euler's rule does hold true. So his rule, or Euler's rule, is that the number of faces of a polygon plus the number of vertices will equal the number of edges plus 2. That's all there is to Euler's rule. In section 10.6, we're talking about both the surface area and the volume of a sphere. When I put this particular piece of clip art into the page here, it looked like it was supposed to work out to be a sphere, but obviously it didn't. So let me put into this or onto this drawing some elements that might add to our dimension here. Okay, let's, if I sort of circle it like this, and then go back behind it a little bit, that kind of gives it a little touch of dimension and shows you that with the sphere, I'm really looking at a ball. Okay, so I'm in 12-6, and I'm looking at spheres, and a sphere is really, for our purposes, it's a ball. All right? Now, you see that if this is the Earth that I'm looking at, that circle that goes right around the fattest part of my circle, the equator part of the Earth, that's called the Great Circle. It's the biggest circle you can get by running a plane through a sphere. So we have our Great Circle, which is like an equator. And we get the radius of the sphere by finding the radius of the Great Circle. So the radius of our sphere, use subscripts, radius sub sphere equals radius of the Great Circle, or an equator. That was written so little that doesn't look really neat to me. Let's make that a little bit better. Great Circle. Okay, so if I'm looking for the radius of this sphere, which I'm going to need to know for my formulas for area and for volume, that's going to be my radius of the Great Circle. It also makes it the radius of our sphere. Okay? Now, we don't have lateral area and total surface area for a sphere because a sphere doesn't have a base, does it? It's just an orb. It doesn't have any base. So we're just going to have two formulas to remember. And those formulas we will begin with are first the surface area, or the area of the sphere. So the area of our sphere is 4 pi r squared. Now, how do we remember that? There are a lot of ways we could develop that, and there's a great explanation on page 880 in your textbook. You can look over and see how it's developed. But when it just comes to memory, how I remember it, you see that this looks like it's 4 circles, 4 pi r squares. So I think about the Earth, and I think about the 4 directions of the Earth, the north, south, east, and west. So I think about 4 circles, 4 pi r squares, giving me my area. Now that's how I remember it. You don't have to use that little technique if you don't want to, but that's just how I keep it straight from some of the other formulas. But again, there's a beautiful explanation on 880 that I think will help maybe just lock it into your memory. But in addition to our beautiful little area formula, we also have the volume formula. So how much does it take to fill up an orb? Well, my volume is 4/3 pi r cubed. Okay, 4/3 pi r cubed, where again r is the radius of my sphere. So here are our two formulas we're going to be using this time. Also, one more thing I want to add before we look at an example or two is remember that if I cut a sphere at the equator part, at the Great Circle, then I have 1/2 of a sphere, and that is called a hemisphere. I know you know that word, probably from social studies in like 7th grade, where you studied longitude and latitude and all of those nice terminology. But I just wanted to call that to your attention and make sure that you were reminded of that vocabulary term. All right, now I want us to look at a couple of examples for area and volume, and then we're going to move on to section 12.8. So here we have another sphere. And notice in your book, sometimes I've had students tell me it's difficult to tell whether they are referring to a radius of a sphere or the diameter of a sphere. So let me just give you a little piece of advice here and show you how the book interprets this. I'm looking on page 884 at number 1 on the exercises. They have the center of the sphere, and then they have a red segment out to the edge of the sphere, and they say that that's 9 meters. That is definitely supposed to be interpreted as the radius of that sphere. So if I want to find the total surface area of that sphere, that's where I'm going to use my 4 pi r squared, 4 circles. And I'm just going to plug in for that r is 9. So I'm going to have 81 times 4 pi, and I'm just going to put that into my calculator. Now again, put it in my calculator again before I was done with it. Again, the most accurate answer is 324 pi. But on these directions in your book, they've asked us to the nearest tenth. So we're going to comply with their request. We get about 1,017.9. And again, this is surface area, so this is square meters. Okay, but now if we have a circle like on number 19, one like I have assigned for you tonight, and it has the whole red piece going across. Something like, well, I'm sorry, that was supposed to go through the center. And it just has like maybe 12 meters. And even though that 12 meters is just on one side of the diameter, since the whole red line is in there, they're meaning for you to take that, to interpret that the whole diameter is 12. Okay? They can't put the 12 all the way, up and down the segment, but that's what they mean. If they have drawn the entire segment, unless they have one little something drawn, which I don't believe they do, they mean for that entire segment to be interpreted as 12. Okay? Let's just use that same example and find the volume. If I'm going to find the volume of this little guy, how much does it take to fill up my little my little sphere? Then I'm going to use my volume formula, which that's our 4/3 formula that for some reason it seems like it's hard to remember for some kids. So if you can think of some really neat way, a mnemonic device or something that would help your classmates remember this, share it with us. And I'm sure that it will be appreciated. Okay, so this time we just had to plug in the radius again now. Forget the one that I put up here, okay? I was just demonstrating something else there. Let's go back to our 9. So this time our volume is 4/3 pi times 9 cubed. Do you all know how to do cubed on your calculator? I guess it's a little late for me to be asking you that. There are 2 ways you can do that. You could put in the 9 and then you can go up arrow, which is the key over the division sign, and put in 3 and hit enter, and you would get 729 that way. Or you can always go to math, and then you can go down to number 3. That's taking the 3rd power of a number. So you would put in 9 first, and you would go to math and go either arrow down or hit the number 3, and that would take your number to the 3rd power. So 2 different ways there that you can take something to the 3rd power quickly on your calculator. And again, let's remember our units. We're talking about volume, so this time we're talking about cubic units. Okay, which is an easy way to remember that cube there is because we're talking about cubic units. Okay, any question there? Please send me an email or a text or a message in some way so that I can know that you have a problem there. What if we wanted to find the dimensions of a hemisphere? Let's look at what we would need to do there. let's get a picture of a hemisphere up here. And I don't believe I'm going to be able to draw this very neatly. How do I want to do this? You know what? Let's just, there it is. How about that? There's a hemisphere. And when we've got the back side of it going, let's blow it up a little bit so you can see it. And actually, we can make the back side kind of go like that. So this is a top half of a circle. And let's say that the radius is, 6. We'll call it just 6 meters. Okay? Now, if I have this and I want to find my surface area, I'm going to use, to find my area, my formula is 4 pi r squares, like 4 circles, remember, and I just have to square the 6, so 4 times 36 pi. But since I'm having a semicircle here, I'm really going to just be taking half of this guy. So that's going to be 72 pi's. I'm putting it in your calculator to get a round off version. Okay, so don't forget just to take half of your area. Now, you know, a lot of books and teachers would make you learn semicircle is 2 pi r squared. I'm just not going to do that. I think you can find the area and just take half of it. I think that you are bright enough to find that along the way. For the volume, since I have 4/3 pi r cubed, and I'm going to take half of that, see how that's going to really be 2/3 pi r cubed? Again, you can figure that out, I know, when you plug it in. So you can 2/3 pi and then put in your radius. So knowing your radius is really the only key thing about the sphere. It's a very easy three-dimensional figure for you to deal with area and volume. So if I'm not mistaken, I think you're going to be fine there to do the assignment for 12.6. So let's move on and talk about 12.8, which ties in with something we had in Chapter 11. So in 12.8, we want to talk about the scale factor and how the scale factor compares with volumes. So let's backtrack a little bit, and let me put a couple of figures up here that we're going to call similar figures. So let me put that over there, and let's put another one of those guys up here. It's a little bit bigger. Okay, so I'm going to tell you these guys are similar. So they're similar to each other. They are similar to each other. And let's say the height of one is, what number do I want to use? The height of one is 2. It's something darker than that, don't it? And the height of the other is, let's say, 5. Okay? And I'm telling you these are similar. So the single dimensions, the linear measures, the radius, the diameter, the height, altitude, all of those measures are going to be just those linear measures. We know are going to have a ratio of 2 to 5. Then when we talked about area, I know that if I want to compare the area of these, the area scale factor since area is in square units, I take my linear scale factor and I square. So my scale factor for area would be a 4 to 25 scale factor. So if I want to know the scale factor for my volumes, Then I go back to the original linear scale factor, and I'm going to cube each one of those because volume is in cubic units. So the scale factor of my volumes would be 8 to 125. Now, if you will remember, sometimes we were given the areas in chapter 11, and we took those areas and found the scale factor. Then we had to take the square root of that scale factor to be able to use our linear scale factor and compare sides, radii, diameters, etc. So I hope it stands to reason that if you are given the volumes of two solids that are similar to each other, that you can compare those volumes and reduce that comparison to find out what your scale factor for volume is, then take the cube root to go back and find the scale factor of your linear measures. Okay? Now, if you would look on your calculator, if you will go to math and down to number 4, you will see is your function to take a cube root. Now remember, taking a cube root of something is the same thing as taking that something to the 1/3 power. So you can enter that into your calculator whichever way you want to. Okay, so if I take 8 and I take the cube root of it, I will get 2. And if I take 125 and take the cube root, I'm going to get 5. So this is the exact same thing that we did in comparing areas. Exactly. We just have to remember that when we are dealing with volume, we have to cube the linear to get to the volume. And if I know the comparison, the scale factors for the volume, I need to cube root to get back to the linear measures. Okay? Since we have had that before, I think you're going to be in good shape there. We do have a couple of, we do have a couple of composite figures on page 900 that you're going to get to work on. But remember that as you work on these, I have already attached the corrections to, I don't believe it's today's lesson. I believe it's Tuesday's lesson. So everything is attached for you. I couldn't download it into the Google Classroom. For some reason it was rejecting it. But I was able then to go ahead and put the PDF attached to your assignment. So you should be able to find that easily. Okay, I'm looking at the wall to make sure I have everything off the board that I promised you I'd put in this video. We've gone over 10.6 and 10.8. Your 12.6 and 12.8, our 12.5 homework is taken care of. We've talked about Eulers. Okay, looks like you're in good shape now to do your homework on 12.6 and 12.8. When you finish that, work on your project. It's due on Tuesday, the 9th. Remember, you do not have to include truth tables. We'll go over truth tables next week. And I think you're ready to roll. So I will see you next week. Have a good weekend, everybody, and good luck with your assignment.